Hi, I'm Rodrigo Obando. I'm a professor at Columbus State University, and I am presenting Cellular Automata rule-generating polynomials. So I want to talk about Cellular Automata rule-generating polynomials. Let me see. There you go. And the abstract, you can read through that. But basically, what I wanted to do is the following. I've been working with Cellular Automata for some time, and normally what we've done with Cellular Automata, we're all only interested in the output of the function that is used in the rule, and all we have is a map. You know that for this combination of input, this is what you get as an output. Great. But there are certain things that I will be interested in and see what kind of functions actually generate those particular outputs. So I started looking into that, and of course, the Boolean function in Mathematica actually does that for you. It can actually tells you, for k equal to 2, Boolean function, it's actually able to give you the polynomial that actually generates the function. That's good. But then, of course, I work in k equal to 3, 3 values, 4 values, whatever number of values. And of course, the Boolean function doesn't work for that. So I got interested. Actually, I did this, in the spring, and I said, how would I do that? How would I actually go ahead and, and create this? I know that there can be any kind of functions that will generate those outputs. So I decided to, sort of start with that, and then I did that, so here's I was doing the introduction, showing the abstract. I'm sorry about that. So my question was, how can I find those functions? And I started looking into it, etc. And I decided to say, okay, let me try using polynomials, to find a one variable modulo k functions. I started doing that, and I said, so if I have this particular coefficients with the x is equal to that, I think I'm able to solve for that, and I was able to do that, and of course, this is in particular for k equal to 2. So that was this was my initial attempt. Actually, I kept it so that you could see all the sort of intricacies of that, and then I realized that I can do that. This is actually very nice. Um, then I found that in order for you to do this, for more variables, etc., that you actually create a what is called a van der Waals matrix. I'm not going to go into that at this moment, but you can look it up. And I said, I can actually do this and generate the given the output vector, I can generate a possible function that would generate that. And when I did that, and it actually worked out okay. And this is the output functions for one variable polynomials modulo 2. That's not very interesting. The 1 plus x is actually x complement, because, for the plus 1, it will complement it. But then I tried that for one variable polynomials modulo 3, and that was actually also possible. That was very nice. It says 27 of those. And then I got all excited, and I said, man, I can now, take a look at the possible function polynomials that I can plug in here, and then I can look at them. It's not just an output; it's actually a polynomial that generates those particular outputs. And of course, I continue working with this, and I tried that for modulo 4, and oops, doesn't work. It happens that for a composite k, for the value number of values for the rules, not all output vectors have solutions. In fact, remember that for every one for a particular one of the solutions, you actually found that they all sort of collapse into one. So my 256 polynomials for modulo 4, one variable, it actually collapsed to 64. I said, oh, and I realized that And I actually continued doing that. I did that for 5 and it worked. I did that for 6, didn't work. And then it started to sound familiar. And then I realized that, oh, with if K is prime, it actually works. Why? So I said, let me see, because now that I see this and I saw that, I said, so all possible, I came up with this problem. It said, all possible modulo K one variable functions can be realized as polynomials of degree K minus 1 if and only if K is prime. And not a mathematician myself, I started to play with this. Um, I'm not a mathematician, but I play one on TV. I'm sorry, but I was interested in this, so I started working on the proof, and then realized that the interesting thing about the Vandermonde matrix over Z of K is that has certain properties. I was able then to look into something like this. I'm not going to go too much into this necessarily, but what I needed to show is that whenever I do this, that the Vandermonde or the transformation B is bijective. It goes both ways, and so in this case, it needs to prove they're both injective and surjective. So I did this proof. I'm not going to go through all the details. I'm still don't like the proof, but uh, is when you have the domain and the codomain, when you can go from one to the other, but not necessarily the other way. That's the surjective part. So you have the one-to-one. So you have the two sets, where they're actually C. So one domain is completely mapped to the other domain, and there is a inverse function that will take you from that domain back to the original domain one-to-one. So there is not a one-to-many or many. Right. It's yeah, both ways. And that's what happens precisely with when the K is composite, is that some of those will actually map to the same on the other side. So they're not one-to-one. So they collapse. So there will be there will be certain set of coefficient in this case that you cannot find them that way. All right, so what I did is, I went through this and I basically, proved that why is it that's what happens, and what happens with the Vandermonde matrix, how it's constructed, we can determine we can compute the determinant, and we know that if the determinant is non-zero, that then the matrix is invertible, is non-singular, and that's what we need. We need a non-singular matrix to go from one to the other one, vice versa. So it happens that when K is prime, in this case, it doesn't have any, it had no zero divisors. And this something like this, I sometimes I struggle with, do I put all these things, etc. But non-zero zero divisors are elements, in this case, on a ring, or not on a ring, but in a group where if you multiply them by something else, the output is actually zero. So even though they are non-zero, when you operate them, it becomes zeros, and that's what's called non-zero zero divisors. And it happens that for primes, that particular matrix, will work because there are no zero divisors. But every time that you do that with a composite number, boop, you have zero divisors. So your determinant becomes zero. So I have this B det, for the Vandermonde determinant up there, but also used the determinant function in Mathematica. And I just sampled through this, and I just wanted to compare whether both of them will actually do that. And you can see the determinant for composite numbers is 0. So that immediately tells me that there is no way that I can express this with the polynomials. So I basically, show that was the case. Then we assume this. So we find that the b to the minus 1, or the inverse of v, only exists when k is prime, and that's basically it. This is how it started, and then actually this goes into now 2-variable polynomials, 3-variable polynomials, etc. But the beginning was, whether I could even construct them, and I can if I do it with k prime. So doing all this, let me see if I can move away. There you go. So for polynomials of higher degree, actually, I continue with this. I have it integrated in a Packlet, which I just published last night. I actually thank, I think it's Todd, for all the help with these things, with the Packlet, etc. So it is now published. Unfortunately, it's still not, it doesn't have a lot of documentation, and I've been working on that. But by the way, might be strange, but I love documentation. I like to have all that, and the way that we do it in Mathematica is actually, I like it very much as well. So when I was going through that, I was struggling whether I publish it or not. They said, no, you go ahead, publish it. The only thing that's going to happen is we're not going to feature it because it doesn't have documentation. So now it is published, and it can be actually used. And all this is actually in that particular thing. So what what I did is, I developed the functions that actually are parallel, or an extension, in this case, to the Boolean function in Mathematica. So in Boolean function in Mathematica, you can pass a rule number, and then you can pass the set of variables, and then it will return back to you the equation that actually implements that particular rule. So here you go. I have the printable equation. I actually wrote that because Boolean function will return to you things such as ampersand, ampersand, or bar, bar for the or, etc. And I don't know. And I know it's correct and everything, but I like to see the pluses and the multiplications in between, and the complements instead of the bang on top of that, or in front of it, etc. So the printable equation actually makes it a little bit more visible. So in this case, I can use Boolean function for that. But for the case of the other one, I actually wrote a function that is called modulus p function. And I tried to follow sort of the same I guess, way of putting the, sort of the same signature, except that because this is not Boolean, I need to pass which modulus I'm using. So in this case, I have the example for k equal to 3. I'm just putting there certain rules, in particular for range equal to 1, and it actually returns to me the polynomials. And I can do this. I was actually the other day using for k equal 23, for 23 values in the cellular automata, and then it gave me very long polynomials for that. So this modulus p function, in fact, I have it so that I have another function that is called rule equation that actually wraps that one into, wraps the modulus p function in such a way that you don't have to provide the variables. I actually have another function that returns the variables. It makes it a little bit easier. So the same rules that I have up there, if I just say rule equation modulo 3 for r equal to 1, here they are. So this particular rule equation in the modulus p function make use of many other variables, which I found useful. What I did is the rule equation is actually composed, it's calling many other functions, because I like to have intermediate results. I like to be able to, in fact, create a hierarchy of functions so that then I can use the same functions in other instances, and so rule variables, you pass the R and it gives you this set of variables. Modulus P core actually gives you the elements or the powers of the polynomial. Let me see. And you provide the modulo, key. In this case, is 3 for R1, which is effectively 3 variables. Then I have also the modulus P matrix. This is the one that generates. This is the Vandermonde matrix that I was talking about before. So when you use this one is the one that you can use. You can invert it, and then you'll be able to go from the coefficient space to the output space, and from the output space back to the coefficient space. And so this is the one. I didn't show anything larger than that, because if I go, with a lot more K, that is, you don't see it. So also there's a function that creates a list of the coefficients, that a given, for instance, a particular number or a rule number. This is in K3, the example, the rule variables for R equal to 1, then it gives you the list of the coefficients. So, that's the reason why I like to do these kinds of things in that I have in between results, because I can use the coefficients. Maybe I don't want to look at the equation. I just want to look at the coefficients, and I'll show you an example of that. So there are other, two functions that can convert directly between output and coefficients and vice versa. And so, for instance, is this one here, as you can see here, is the modulus P coefficient that it gives you this. But here I can say from the output this, using 3, 1, this is, it gives me the integer, and then I can expand it. And then you can see it's the same set of coefficients that you see above. Then I have the function that converts a list of coefficients to the rule output. In this case, this is effectively applying the polynomial to generate your output, for the rule. And so you can take this. In this case, I'm taking this number over here, and then I say coefficient to output, and this is the output. So this is the rule number, and these are the coefficients. I mean, this is the actual map of the rule. All right, so can I do this? There you go. So of course the question came. It says polynomials for composite K. What do we do with those? Because these polynomials do not work with that. I don't have it yet, but I have a work in progress where, in fact, I'm looking into a polynomial of mixed radix, so that you can create a polynomial where parts of those are of a particular K, or not K, but modulus, and other parts is another modulus. So in this case, if I take, for instance, K equal to 4, I get I factor, the factors will be a 2 and 2. So I know that I can create the polynomial using 2 combined polynomials modulo 2. And that allows me to do that. So when I did it, I tried for 12, and then of course it will give you, I can have 2 polynomials of modulo 2 and a polynomial of modulo 3, and actually solves the problem. But I don't have the answer to that. It's still in progress, but I wanted to show that that's more or less what I want to do. That's the direction I'm going to. So one of the uses, and I thought of that, as a probabilistic cellular automata. I've actually worked with probabilistic cellular automata. I had a student, and he and I worked on this. We actually present some things back in 2016 or something like that, where we took the output of a rule, and we made some of the outputs to be random. Sometimes it will be 1, sometimes it will be 0. And this will be actually executed every time that you run the cellular automaton. It will evaluate that. So for every cell, for every step, it would change the rule. It actually created very interesting things. But that's actually working directly on the output. My question was, if I have the polynomial that generate this, can I then simulate, have a system that in fact is taking inputs, and those inputs are my coefficients in the polynomial. And then I take one of those or more of those coefficients to be random variables. What kind of behavior am I going to get? How is it that I want to see? What kind of behavior I'm going to see on the evolution of this of cellular automata? So I actually, I thought of this. I put it in there, and when I came here, not last night, but the night before, foolishly, I decided to say, that would be interesting. Let me see if I can do it. And actually didn't sleep very well of that night because it was not working as I wanted it. But I was able to actually do that. And I said, and fortunately it works. And I'm able to show you here. So this P rule actually takes a set of coefficients, has a set of coefficients, which coefficients will be random. Of course, takes a K and takes an R, and it actually generates a rule using, it's funny, it's a rule using rules. I don't know if you ever use cellular automata. Normally, we actually just put an integer in there and they just let it play. But there are other ways to show that. It's actually saying, okay, for this particular input, I want this output. So the trick with this, and I actually learned this from Jessica Doman. She used to work for Wolfram, some years ago. The thing with this is actually you leave something that does not evaluate. And this is why you have this over here, that you do not evaluate, that this assignment, it only gets evaluated when it gets sampled. And then it actually works. So anyway, I don't have much time for this. So what I did is I created a manipulate. And this manipulate over here, I'm taking the ECA. This is, in fact, I took rule 90, which, is very symmetric. And you can see here, these are the variables for the polynomial. And this over here is the coefficients. In this case, I have 3, the coefficient number 3 to be random. And on the right, you see the output of that particular cellular automata, which looks to me a lot like rule 30, doesn't it? It's a random. Actually, it's more random, in that sense. So you can actually take, another, click on another, click other. Let me see. There you go. You can click other variables, all the other coefficients to make it random, and you end up with interesting behavior. So here I'm going to go to something that hopefully many people know about. This is rule 110, and that's the behavior having this. So let me maybe remove this, and then you have that, or maybe do this one here, do this one here, then you have all kinds of different behavior. So that turned out to be actually very interesting. Look at that, 30 with 3 and 7 coefficients. When you make them random, this is the way it works, etc. So you can actually play with this. This should be available on my talk. And just to show, This is a manipulate where I'm actually doing this in k equal to 3. And you can see the probability on the right. This one, I didn't have the way of just going through each one of those because it turned out to be 7 trillion possible rules. So, you can actually try putting any number in there and then you will see it. I don't have a way of determining the coefficients either. I didn't, it's actually 27. Yeah, a lot of coefficients. Now I remember. Yes. So this here is just 3 and 5. So you can change the rule and then see that. So it turned out to be, at least I was successful in doing this. All right. So just as a conclusion, that is actually finding the polynomial, that defines the rule function of a cellular automata allows for all the kinds of analysis of cellular automata behavior. It provides a new avenue to explore many types of cellular automata from the point of view of the polynomials and not just the output, that's what been done all this time. Now, this also plays an important role in a unified model of cellular automata that I'm presenting today. So this is my plug for today at 1:30, same room. In fact, as I said last night, I published the package, but all that is like a 10% of the package. The functions are actually available in this because I wasn't sure whether that was going to be published, but you can play with those, and they are actually right here. So these are standalone right now. These are the ones that are actually you're able to do all these kinds of things. And now I'm just open for questions, even though I know I just have like 3 minutes left. But I appreciate. Thank you.